Today we're going to talk about magnetic flux. There's a few key questions we need to answer here. How can we calculate magnetic flux? And first of all, what is magnetic flux? Remember, when we're talking about magnetic flux, a change in magnetic field can cause an electric current to flow. This is electromagnetic induction. So, how does this happen? The change in magnetic field causes an electromotive force, or an EMF, to appear in the wire. An electromotive force is the difference in potential that causes an electric current to flow. So, going back to the question, what is magnetic flux? This is the size of the induced electromotive force. An example here. It's easier to understand with an example. So if we talk about a coil of wire, like shown, and the area, which is in grey. This we calculate in meters squared. And we pass magnetic lines through it. So the density of these magnetic field lines is also known as the flux density, which we give the symbol B and is measured in Tesla. Here we have a key formula. Phi is equal to B times A. So the first symbol there is phi, which is magnetic flux. And we measure that with the unit Weber, capital W, small b. Note, this only works if the magnetic field lines are perpendicular or passing at right or 90 degrees to the surface A. It doesn't work entirely if it's not at 90 degrees. So example 1. What is the magnetic field through a loop of 0.4 meters squares placed at right angles to a magnetic field of 2 Tesla? So again, we draw our diagram. Here the area is 0.4 and the magnetic flux density is 2 Tesla. We use our formula. So magnetic flux is equal to magnetic flux density times A. We're trying to calculate magnetic flux. So we submit our values into the formula, 2 by 0.4, and that gives us 0.8 Weber. Simple. Note, if the magnetic flux density is not perpendicular to the area, so if these lines coming in are not equal to 90 degrees, the flux through A is the component of B perpendicular to A multiplied by the area. Okay, this sounds a lot more complicated than it is, so what we're going to do is give an example. So here, what is the magnetic flux through a loop of area 0.4 meters squared in a magnetic field of 2 Tesla if the flux density makes 30 degrees with the loop? So this time we have an angle here. So here we have an area, we have a magnetic flux density passing through, and we have an angle which is 30 degrees. Our magnetic flux is 2 Tesla. And our area is 0.4 meters squared. To make this easier, we'll go and take a bird's eye view of this. So if I was to look directly down on this line here would represent this line there. We still have our magnetic flux density passing through. However, in the note before, it says that you need to get the component of B that is perpendicular to A, so at right angles, which is that line, that dotted line there. Okay, so this is the component of B perpendicular to A. Reminded that our angle is 30 degrees. So, if in yellow that component, then that would be the same either side. So we can actually form a triangle here. From a triangle, we can have opposite, hypotenuse, and adjacent. And we can actually find out the opposite here. So a simple rule to try and remember our sine, cosine and tan rules. Silly old Harry caught a herring trawling off America. Sine, so silly for sine, opposite over hypotenuse, cos equals adjacent over hypotenuse, and tan equals opposite over adjacent. For this, what do we have given to us? Well, we have the hypotenuse, that is equal to 2 Tesla. We are not sure of what opposite is, but we are given the degree or the angle to it. So we can use the sine rule. Here we have our triangle again, and we now know sine is equal to opposite over hypotenuse. So sine of 30, or angle, is equal to x over 2. 0.5 is equal to x, which is the line that we're trying to find out, the opposite line, over 2. And 1 Tesla equals x. Now, we now know what B is equal to. But remember, to get magnetic flux, you need to multiply B by the area. So we need to multiply this answer by the area, which is 0.4 meters squared. So 1 multiplied by 0.4 will equal to 0.4 Weber, which is the magnetic flux passing through, or the total magnetic flux. Hope this is of some help.